Hi, welcome back to this cryptography video series. In the previous segment, we talked about a problem related to information leakage in the counter mode. In particular, the length of the plain text was revealed from the ciphertext. And in this segment, I will show you how we can add padding to the encryption process and minimize the risk of leaking information related to the length of the plain text, which may or may not be a concern. Okay. All right. So if you wanted to minimize the risk of leaking the length of the plain text, the idea of padding is well established in symmetric block cipher encryption mode, and I'm going to apply that to the counter mode. I mentioned earlier that not all libraries do padding when you do AES, for example, in the counter mode. Some libraries do that. Some libraries let the user or the programmer to first pad before calling the encryption layer. So what is this padding? How do we do it? Okay. So let's quickly draw the picture of the counter mode. We have discussed it in the previous segment, so I will not talk all the details. So in the counter mode, we have, say, a counter, which is a number. It can be random. It need not be random, but that's not the main message now. A counter is fed into a block cipher. It could be AES, or it could be any pseudo-random function for that matter. It need not be invertible because we can use the same circuit for encryption and decryption in the counter mode. That's one of the nice benefits. We will get out some stream of secrets. Let's call it S0, right? And this S0 will be XORed with your M0. So M0 is the first block of your message. Message itself is partitioned into blocks, right? So let me write it here very quickly. M equal to, say, M is your message. Let's say it's made of two blocks, M0 and the M1. Each block, if you're using AES, each block can be 128-bit. Okay. All right. So this is how the first block will be encrypted, and we get the first block ciphertext C0. So what about the second block? The second block is basically the same circuit. Instead of counter, it will be counter plus 1. And the reason is that since FK is a pseudo-random function, incrementing the counter by 1 should give you a completely garbage output. So the stream of the keys are not necessarily comparable in the sense that they look very random. So we get out, let's call this S0 stream, and this is S1 stream, right? You get a stream of secrets, and that stream is going to be XORed with your second block of message M1, and you will be XORing it like this, right? Okay, so your XOR needs two inputs. Okay, it's not a pretty picture, but that's fine. So you get out C1. So the question now is, what happens if your message, say, this is 128-bit, right? And this is not 128-bit. Let's say this is just 120 bits. Okay, that means we have 8 bits to throw off, right? We have to throw that off from the stream S1, and then we can XOR it. But that will leak the information to the cyber cryptanalysts that we are sending a message made of 248-bit. Okay, so how do we minimize that risk? As I said, that may not be risk always, but if there are cases where it makes sense to hide the length of exact length. You cannot hide the lower bound. You can only hide the exact length. Okay. So how do we hide that? One possibility is before we call the encryption function, what we will do is we'll take M1, right? We look at the M1 length. What is the M1 length in our case? This is 16 bytes, right? 128 bits means 16 bytes. This is 15 bytes. So what we will do, we will append a padding byte. Okay, so the idea of padding byte is extremely simple. Say you have a message. Let me explain the idea of padding. Suppose your message is supposed to be encrypted using a 16-byte block cipher, which means 128 bits. Suppose your data has 15 bytes. That means you have 15 bytes of data, right? So what about, let's say this is byte 1, byte 2, byte 3, and so on, right? And this is byte number 15. So what you do here is that here is a byte number 16, right? So what you do here is just put 1 here, okay? Usually the notation is hex, so you will put hex 1, okay? So what is the new length now? The new length is 16 because we have 15 bytes of message. This is the message and this is the padding, right? This is called the padding byte. So this is pad, okay? So what if your message is say 14 bytes instead of 15? In that case, it follows this nice pattern again. Okay, it's not a pretty picture, but you can still understand what I'm trying to say. So you have say 14 bytes of message, right? What about 15th and 16 byte in that case? You will put 02. Let me put just 2. 2 means in hex 2, okay? 0x02. Now, your first 14 bytes will be, so all the way here, these 14 bytes are your data bytes. The last 2 bytes are your padding bytes, okay? But there is another question. What if the message itself is a multiple of block size? Let's say the message is already perfectly aligned. In that case, you still have to pad, otherwise the decryptor wouldn't know how to carefully decrypt it and throw away the last bytes, right? The padding tells you exactly how many bytes have to be thrown out. That's the idea of padding. So what you do in that case is you basically repeat another block. Say the message that you're trying to encrypt is 1 block, 16 bytes. So what you will do in that case is you will keep the message as it is, but you will be adding another block called padding block. It's just waste of space, but still you have to add it for successful, consistent decryption. So if you want to hide the exact length of your message, okay. So what you will do in this case is you'll have 16 bytes. You write everywhere in hex 0 or 10, which means 16, right? 10, 10, 16 times you would be writing this, and so on, 16 times, and then you have this. So now your message is actually, this is the message, okay? And when the decryptor decrypts it, he knows how to get rid of the padding byte, because all he has to do is he looks at the last, or he or she looks at the last padding value, and he knows how many bytes have to be discarded. So you'll discard that many and then give you back the actual message. So that's the idea of padding. There are multiple variants of this padding idea, but this is basically one of the frequently used padding. As you probably know, in CBC, for example, this is the padding style. Okay. Now let me show you some quick demo of this padding idea. Okay. So what I'm going to do is basically show you my my implementation a little bit, not so much. I'll do a share. Okay, so what you're seeing here is, oops, one moment. What you're going to see is the effect of padding, okay? In the previous demo, I showed that without padding, the information is leaked. Now we will run with padding, okay? Say, I call it, this is a little program that I wrote. Let's say we encrypt yes, okay? Yes is made of 3 characters. You'll see what the output is, okay? You see here, this is the output ciphertext, okay? Don't worry about the last line. This is the, we can even remove it one moment just to be clear. Okay, so we can leave this. We don't need to decrypt at this point. I will enable it in a moment later. So first, let's just compile this thing. I'm going to run the padding demo, right? Of the message yes. Yes is made of 3 characters. But if you look at the ciphertext, and I have already counted it for you, it's made of 16 bytes. We can check it quickly. Okay, so 32 ASCII characters means 16 bytes. So let's do the same with no. It's also, as you can see, it's the same length. Although our input has different lengths, we get the same ciphertext length. Okay, this is how we hide the length, exact length of the plaintext. Just a piece of warning, not related to cryptography per se, is that you're not supposed to pass secrets via command line arguments like this because it's part of the history. But for demo, I decided to do like this. Otherwise, you would be passing via runtime inputs. Anyway, that's basically the idea of this padding. The padding is essentially trying to hide the length of the plain text. So what happens during decryption then? Will the decryptor carefully remove it? Of course it will, because the padding scheme is very consistent and clear how to interpret the resulting resulting plain text. Okay, let's decrypt it, and it will be printed in ASCII, but I will read it for you. Okay, that's not a problem. So I will be compiling this again because I just enabled the decryption, and let's do simple encryption. Let's encrypt ABC. Okay, ABC in hex means when we decrypt it, it's 41, 42, 43. That's perfect. So as you can see, although our ciphertext is longer than 3 bytes, during decryption, we carefully remove the padding bytes and get back exactly the original bytes we wanted. Okay. What about AB? AB should also have only 41, 42. Yeah, it removed. So I used Java's counter mode example. Let me show you the counter mode instantiation very quickly. So I still use AES counter no padding, right? Because as far as I know in Java, there's no notion of padding in counter mode. So what I did is instead of directly passing my text to the Java cipher, I first do a padding. So I'll briefly explain the padding idea very briefly. There are things that you have to check. I didn't necessarily check every use case, every corner case, but what I do is I basically take the plain text and measure how many bytes I have to pad. This logic will do that. I haven't checked all the corner cases, but anyway, so you get the padding length, and then you create a pad array, right? Pad array, just put the same. See, if you have to pad, say 16 bytes, you will put 16, 16, 16, 16 times. And then you will take your plain text and append it to the padded plain text, and then you call the encrypt function. Essentially, that's basically what this portion of the code is doing. So it appends the pad bytes to the plain text, and then during decryption process, right? All we do is we decrypt first, right, and then we get rid of the padding. So you will get into padding oracle problems also here if you don't handle the exception properly. I will talk about padding oracle attacks later about the counter mode. Okay, so as you can see here, we throw away the padded bytes after checking the padding. Here is this logic. Essentially, it takes the length of the ciphertext and then subtracts the padding. After we pad, after we decrypt, we know where how many bytes are padded. Therefore, we can throw away that many bytes. Okay, this is basically what's happening here in this part of the code. So that's all actually. Not that difficult to add padding to the plain text. If you wanted to hide the length of your plain text for whatever reason, for privacy reason, there may be scenarios where the length of the plain text reveals, length of the ciphertext rather reveals some information about the plain text. In that case, we have to do some kind of padding, like the padding that I have shown you is the standard padding used in CBC mode, for example. Okay. All right. So in one of the future videos, I will show you how you could perform padding oracle attacks on the counter mode as well. Thank you.